York University is excited to present Examining Autoexposure for Challenging Scenes. We examine autoexposure by making three contributions. First, we captured a 4D exposure dataset that contains challenging exposure sequences. Second, we created a platform that allows us to evaluate different autoexposure algorithms on this dataset. Finally, we evaluated 4 different autoexposure algorithms. Our motivation for this work is that autoexposure currently fails under challenging lighting conditions. Challenging lighting conditions arise from backlights, spotlights, moving lights, flashing lights, and the movement of preferred objects in the scene. Working on autoexposure requires data that contains dimension over time and exposure, a 4D dataset. However, existing datasets contain an exposure dimension but lack a time dimension. To solve this issue, we captured a 4D exposure dataset with dimension over time and exposure. We do this by using a stop-motion setup that consists of controllable stages and lights. We can use this setup to capture exposure stacks. Exposure stacks are images of the same scene captured at a range of exposures. For each scene, we capture 100 time steps using stop motion. For each time step, we either adjust the linear stage to move objects or lighting in the scene, or we adjust the lighting by turning lights on or off. For each scene, our 4D exposure datasets consist of 100 time steps at 15 different exposures. Here, we show a demo of our 4D exposure dataset. Our exposure dataset has dimension over time, but it also has dimension over exposure. Our dataset consists of 9 scenes captured with a combination of challenging lighting conditions. Additionally, we created scenes with reflective or preferred objects. We created an autoexposure platform that allows others to easily work with our dataset. This platform allows for simulation of different autoexposure algorithms on our dataset. Additionally, the platform can be used as a dataset explorer as it allows the data to be navigated over exposure and time dimension. We use our dataset to examine 4 different autoexposure algorithms: a global method, a saliency method that we propose, a semantic method, and an entropy method. Most autoexposure algorithms are histogram-based. In our evaluation, the global, semantic, and saliency methods are histogram-based. Histogram-based autoexposure starts with an initial image histogram being manipulated by an algorithm. Then the mean of this manipulated histogram is driven to a set key value by modifying exposure. This key value is a calibrated raw value which maps to images at half brightness in the final post-process color space. The global and semantic algorithms are quite similar. The main difference is that the global algorithm considers the full image while the semantic algorithm considers just a specified region. Both algorithms build histograms, and a common step of clipping saturated pixels is also performed. Our saliency autoexposure algorithm uses a saliency map to build the modified image histogram. We create the saliency map using a fast saliency detector. Then, this saliency map is binarized using a threshold. We use the previous frame saliency map to re-weight the current image histogram. Again, we remove saturated pixels in the image histogram. Entropy autoexposure algorithm is based in the premise that the best exposed image has the highest entropy in sRGB space. Since we have access to a full exposure stack, we can compute all entropies within the stack. The exposure with the highest entropy is considered optimal by this algorithm. We can simulate videos for each algorithm on our 4D dataset by applying the algorithms at each time step. Here, we show some output samples of these 4 autoexposure algorithms on 4 different scenes. We then conducted a forced choice user study to compare these algorithms. we found that our proposed saliency method was ranked the highest. The reason users seemed to prefer the saliency method was because in challenging lighting, the saliency algorithm would differ from traditional methods like the global algorithm. This is because the saliency method prioritized objects like the globe over the background. In summary, we captured a new 4D exposure dataset that provides dimension over time and exposure. We designed a software platform for auto-exposure algorithms to be simulated with this dataset. We examined 4 different auto-exposure algorithms on our dataset, and we found that users preferred a simple saliency method.